Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. Group 2. Starting with the basics, electron configurations. Here are the first four elements: beryllium, magnesium, calcium, strontium. Their atomic numbers. Write electron configurations in terms of shells for each of those four and then as subshells. Pause the video, complete the task, come back when you are ready to check your answers. So here is the electron configuration for beryllium, 2 and 2, subshells 1s2, 2s2. Magnesium, 282, subshells 1s2, 2s2, 2p6, 3s2. Calcium, 2882, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Strontium, 2818, 82, subshells 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2. Now, if you have written 3d in a different position after 4s, that's fine, because of course 4s is filled before 3d. What do we see in common is that the outer shell, the highest energy subshell, is always of the form S2, an S subshell with 2 electrons. So we can write a general statement for group 2 that the outer shell of a group 2 element corresponds to NS2. Having discussed electron configurations, let's move on to the way group 2 elements react. And they all react in the same way. And if they react, they always do this. They lose 2 electrons to form the 2+ ion. Now, in terms of redox chemistry, oxidation and reduction, at least 3 things can be said interpreting that equation. Please pause the video, think back about redox chemistry, and write down what you can about group 2 redox chemistry. Okay, so the first thing we can say about group 2 is that their oxidation number is always +2 in compounds. If they always form 2+ ions, then they're always going to have an oxidation number of +2. Please note, the oxidation number is indicated by the plus in front of the number. Now, if they react by losing electrons, then group 2 elements undergo oxidation. If they themselves undergo oxidation, the loss of electrons, something else must be gaining electrons, so group 2 elements are reducing agents. Now, if they form 2+ ions, I'd like you to write the configuration of a couple of group 2 ions. Could you write the electron configurations in terms of shells and in terms of subshells for magnesium 2+ and calcium 2+? Pause the video, complete that task, restart to check your answer. So here are the answers. Magnesium 2+ has lost 2 electrons, of course, so it's 282, 1s2, 2s2, 2p6. Calcium has lost 2 electrons, so we've only got 18 to accommodate. 288, 1s2, 2s2, 2p6, 3s2, 3p6. By losing 2 electrons, they achieve a noble gas structure. In this case, neon for magnesium 2+, and argon for calcium 2+. Looking at some particular reactions of group 2 that are specified by OCR A, the first one being the reaction with oxygen to form simple ionic oxide. So the equation looks like this. I'm using the symbol M to represent any group 2 metal, so that could be calcium, barium, magnesium. Reacting, so 2 moles of the group 2 metal react with 1 mole of oxygen gas to give us 2 moles of the ionic solid MO. So that could be MgO, CaO, BaO, etc. You need to write the relevant redox half equations. So the equation that's written on the screen there is a redox reaction. There is an oxidation and a reduction taking place. Can you write half equations to represent the oxidation and the reduction? Pause the video, complete the task, come back to check your answers. So here is the oxidation. Of course, the metal is oxidized. We discussed earlier that the reactions of group 2 always involve the oxidation of the group 2 element. So the metal M loses 2 electrons to form 2+ ions. And that must mean that oxygen is reduced. That is, the oxygen, each oxygen atom gains 2 electrons to form the oxide ion. And that pattern is followed for all of group 2 elements in their reactions with oxygen. Moving on to the reaction with water, again specified in OCR A chemistry. The products are an ionic hydroxide, metal hydroxide, and hydrogen gas. Pause the video and write a balanced chemical equation for the reaction of group 2 metal with water. So, if I show you my equation, we have a metal to form and liberate hydrogen gas H2, and then we need to get the formula of the ionic hydroxide correct. This can be a problem. We know that group 2 metals form 2+ ions. Hopefully you are aware that a hydroxide ion is a 1- ion. We'll see that one of each don't produce a neutral compound, so we need an additional hydroxide ion so that the ion charges sum to 0. So our formula of the metal hydroxide is MOH twice. Now, just as before, we can interpret these in terms of redox half equations. So please pause the video and write 2 redox half equations, an oxidation half equation and a reduction half equation. Resume when you are ready. So here is the oxidation, always the same. The metal goes to metal 2+. The reduction, however, is slightly more problematical because we are going to reduce only some of the hydrogen from within 2 water molecules. The oxidation number of hydrogen within a water molecule is, of course, +1. In the elemental state, it is 0, so 2 hydrogens have been reduced. The 2 remaining hydrogens stay at oxidation number +1 and combine within the hydroxide ion. Now, a useful guide to this, as with a lot of other redox equations is to look at the overall charge. The overall charge on the left-hand side is 2 minus. The overall charge on the right-hand side, therefore, must also be 2 minus. So we need 2 hydroxide ions to balance that equation. So total charge on the left-hand side, neutral water and 2 electrons, 2 minus. H2 and 2 OH minus, also 2 minus. So we are balanced for charge. Just to repeat, only some of the hydrogen within 2 water molecules, or more specifically 2 hydrogen atoms from within 2 water molecules, are reduced to form elemental hydrogen. Now we can also consider reactivity. This reaction is often carried out in a school lab. You may have seen barium, you may not have seen barium reaction with water, but you are almost certainly will have seen calcium's reaction with water. It gets pretty hot, quite hazardous, and magnesium, slow bubbling. So there's a clear trend in reactivity in group 2. At the bottom of the group, barium far more reactive than at the top of the group, magnesium. Now, if you haven't seen those in your school lab, I suggest you might Google reactions of group 2 with water and look at some YouTube videos. There are lots to choose from, including most probably some of my own. The third reaction is with dilute acids to form the salt and hydrogen gas. So if we take hydrochloric acid as our model acid, pause the lesson and write an equation for the reaction of a group 2 metal with hydrochloric acid. Resume when you are ready. So here's my equation. Hydrochloric acid HCl. We form the salt MCl2, which will be, of course, aqueous, soluble, and of course we have hydrogen gas, H2. Now, a salt is formed by the reaction of a metal with an acid, and the hydrogen from within the acid has been replaced by the metal itself. So that's our definition of a salt. The hydrogen from within the acid is replaced by the metal within the formula. Now, of course, we can also look at redox half equations. So could you write an oxidation and reduction half equation for the reaction of group 2 metal with a dilute acid? So I'm going to reveal my equations. As always, the reaction of a group 2 metal, the metal is oxidized to a 2+ ion. The acid provides hydrogen ions, H+, which gain 2 electrons to give us hydrogen gas. So there is our reduction. But I can also bring in a quick review of ionic equations here. So could you write the ionic equation for this reaction? Pause the video, come back when you're ready. So here is the ionic equation for the reaction. You can see that we've got our 2 reactants from the redox half equations, the metal and the 2 hydrogen ions, forming the 2 products from the 2 half equations, M2+ and H2 gas. You might ask, or might need reminding of, what's happened to the chlorine? Well, we've got chlorine in the full equations, but the chlorine is acting as spectator ion. It does not change. We've got a chloride ion here at -1 and a chloride ion here at -1, or 2 chloride ions on the left hand side and 2 chloride ions on the right hand side. They have not undergone any change. They are spectating. So they are not included in the ionic equation, which is simply the sum of the 2 redox half equations here. Now this reaction also very clearly shows the trend in reactivity. barium is the most reactive, magnesium is the least reactive. There's the trend as before. At the bottom of the group, much more reactive. At the top of the group, much less reactive. However, you wouldn't be investigating these reactions. Calcium with an acid, for instance, is pretty dangerous, so maybe too hazardous. You may have done calcium, but you certainly wouldn't be looking at barium or strontium or with a dilute acid. At this point, it's worth recapping with a few basic problems to solve. So write balanced symbol equations for the reactions of calcium with oxygen, with water, sulfuric acid and nitric acid. Pause the video, restart when you need to check your answers. So for oxygen, 2 calciums give us 2 calcium oxides. I've included state symbols. If you haven't done, perhaps quickly add your state symbols. Maybe you need to pause and add your state symbols. With water, calcium, we get our hydroxide and hydrogen gas. With sulfuric acid, we get calcium sulfate and hydrogen gas. And with nitric acid, we get calcium nitrate and hydrogen gas. We can also confirm the trend in reactivity down the group, not just from observation of test tube reactions, but also from some data. And that data, of course, is ionisation energies. Just to remind you, the reaction of group 2 metals is always the formation of a 2+ ion. Well, we've got data on the formation of a 1+ ion, the first ionisation energy, and we have data on forming a 2+ ion from that 1+ ion, the second ionisation energy. So if we look at this table here, we've got the elements of group 2. The first ionisation takes the gaseous atom to the gaseous unipositive 1+ ion. The second ionisation energy takes that +1 ion and turns it into a 2+ ion. And we can find that data for each element in the data books. If we add them together to give the total energy for the change gaseous atom to gaseous 2+ ion, then we can perhaps see a trend in the energy needed to achieve that change. If I reveal the totals, you will see that to form a 2+ ion from the gaseous ion for magnesium requires, it's 2,189, these energies are in kilojoules per mole. But for barium at the bottom of the group, only requires 1,468. There's clearly a trend going down the group of decreasing total energy needed to form the 2+ ion. In other words, increase in reactivity. So we've got 2 sources of information that tell us about the reactivity trend down group 2. Firstly, our observations of the test tube reactions, which you are expected to recall. And secondly, an interpretation of the first and second ionisation energies, adding them together to achieve this change that I'm highlighting here, and then noting that a lot more energy is needed to achieve that change for magnesium than for barium. And it's that change which takes place when group 2 metals react. There are also some reactions of the compounds of group 2 expected to be known. The first concerns group 2 oxides and their reaction with water. Pause the lesson and complete an equation for the reaction of a typical group 2 oxide with water. Resume when you're ready. So here's my equation. We've got our group 2 oxide, water forming the hydroxide. Now, that ionic hydroxide will partially dissociate in aqueous solution. So we have our hydroxide on the left and our dissociated ions on the right. From your acid-base chemistry, you will know that the release of hydroxide ions into solution produces an alkaline pH. The actual pH of the solution itself is dependent on the concentration of hydroxide ions. And the concentration of hydroxide ions in a solution of any particular group 2 metal hydroxide is dependent on the extent of dissociation, in other words, the solubility. So here we have an equilibrium sign indicating we have a partial dissociation. The more complete the dissociation, the higher the concentration of hydroxide ions. The higher the concentration of hydroxide ions, the higher the pH. So we're going to use those logical steps to solve a problem on the solubility trend for the hydroxides of group 2 on the next slide. This table has the metal hydroxides of group 2 and the pH of the solution they formed. Based on that data, can you deduce a trend in the solubility of the metal hydroxides? Pause the video, think it through, come back to check against my answers. So I'm going to look at the magnesium hydroxide pH, which is 8, which implies that the concentration of hydroxide ions is quite low, and therefore the degree of dissociation is low, and therefore the solubility of magnesium hydroxide is low. If I go to the bottom of the group, we see barium hydroxide, the pH is high, the concentration of hydroxide ions is relatively high, and therefore the degree of dissociation is high. That means the solubility of barium hydroxide is high. So the trend down the group would be that we have the most soluble hydroxide at the bottom and the least soluble hydroxide at the top. I have also some supporting data. So that confirms the solubility trend. We've got a low figure in moles per 100 grams and a higher figure at the bottom. So the trend in solubility is highest for barium hydroxide, lowest for magnesium hydroxide. You are expected to recall that fact and therefore its effect on the pH of the solutions formed. The last item to cover is the use of the basic properties of some group 2 compounds, and these are used to neutralize acidity. There are 2 examples specified in OCR A. The first one is the spreading of calcium hydroxide slate lime on agricultural land that is acidic. Many crops don't enjoy a low pH. If we assume that the acid causing the low pH is sulfuric acid, perhaps from acidified rain, can you complete and balance the neutralization equation? Pause the video, check your answer when you're ready. Here is the completed equation. We get calcium sulfate, the salt, and 2 moles of water. Now the second example of a use is in indigestion remedies such as Alka-Seltzer, Tums, which one can buy from the chemist. These tablets and acid tablets contain magnesium hydroxide or sometimes calcium carbonate or sometimes both. If we assume that the acid causing indigestion in the stomach is hydrochloric acid, HCl, write equations for the neutralization of hydrochloric acid by magnesium hydroxide and by calcium carbonate. Pause the video, complete that task, check your answers when you're ready. So here is my equation for the neutralization of hydrochloric acid with magnesium hydroxide. The products are magnesium chloride and 2 moles of water, and we need 2 moles of hydrochloric acid or hydrogen chloride to balance. And then for calcium carbonate, again 2 moles of hydrochloric acid, calcium chloride the salt, and carbon dioxide and water are the 2 other products. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.